Hello everyone, I'm Colin Kurz, and this is my report for Lab 2. The purpose of this lab is to find the amount of charge held in a strip of charge tape using both a real-life experiment and a computational model. To accomplish this, in the previous lab, a piece of tape was attached at its end to neutral objects, and another piece of tape was raised up from beneath it until the top piece of tape started to float. Calculations were performed to discover the amount of electric force on the top tape, assuming that the tapes were both point charges. The resulting data and calculations were used for this lab. Then, a computational model of this experiment was constructed and used to calculate the magnitude of the charge on the tape. The results of this lab show that the tape had a significant positive charge. The fundamental physics principle of this lab was Coulomb's law. Coulomb's law states that the net electric force acting on one charged particle due to another is equal to a constant k times the charges of the two interacting particles divided by the square of the distance between them. In this lab, the charged particles were the individual particles within the tape. The electric field formula was used to help compute the force at each particle. The lab also uses Newton's first law of motion, as it relies upon the concept that an object at rest must have a force of zero to stay at rest. Essentially, the point when the electric force on the tape cancels out the force of gravity on the tape is when the two forces are equal. This fact will be used to find the electric charge on the tape. Finally, the lab relies on the iteration of the forces of several particles on each other to construct a more accurate net force acting on one object from another. Some values and results from the previous lab were important to this lab, both as a point of comparison and as data used in this lab. Both the computational and physical models found that the total charge on the tape was 7.47 times 10 to the negative ninth coulombs, and some other important constants were noted. The electric force on the top piece of tape was calculated to be 1.962 times 10 to the negative 3 newtons, which will be important as a point of comparison in this lab. The coding required several steps. First, some important constants were established. Next, a function to calculate the electric field at any point in space due to the bottom charges was created, using the formula for an electric field. Then, a function was used to create a line of charge, which is not shown because it was provided. The position and size of the tape in the model were chosen based on the experimental data of the previous lab. The number of charges per line of tape was also chosen. Then, iteration of the electric field and Coulomb's law formulas was used to calculate the electric force on each charge in the top tape due to each charge in the bottom tape, as well as create arrows representing the electric force on each point of charge in the top tape. Finally, the net electric force on the top tape was found by adding together all the iterations. This was displayed as an arrow, along with gravitational force. The electric force was found to be 2.812 times 10 to the negative 4 newtons. The magnitude of the charge on one piece of tape was found to be 2.5 times 10 to the negative 7 coulombs. Comparing the results of both computational models, the magnitude of the electric force was found to be an entire order of magnitude off between them. The difference between the two calculated net charges is similarly large. As seen in the figures, the new model's electric force and net charge were found to be smaller than the old models. It is likely that the new model has the most accurate electric force, since each piece of tape has a distributed charge, as seen in the new model, rather than one point charge, as seen in the old model. Thus, modeling the pieces of tape as distributed charges rather than point charges likely produced a more accurate result. Some important assumptions were taken which may have impacted the calculation of the electric force. It was assumed that each tape was exactly the same length and had the same net charge, which could very well be untrue due to human error. It was also assumed that only electric and gravitational forces were acting on the system. It was not assumed that each piece of tape could be treated as a point particle. Air resistance did not need to be ignored, since the floating tape is at rest and not moving through the air. Some errors may also have occurred. As already discussed, the tapes may have not been the same length or had the same charge due to human error. The tapes may also not have been held or secured correctly for the charges to interact ideally. Some final questions remain. What if you had modeled each of your tapes as a single point charge, like in the previous lab? If each of the tapes had been modeled as a single point charge, then the result have been exactly the same as the last lab, since the same experimental data was used to model each of the tapes as a single point charge in the previous lab. As discussed earlier, the magnitude of the new model's net charge was smaller than the old point particle model. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? The estimates differ because the pieces of tape are not point charges. Their charge is distributed over the surface of the tape, and this distributed charge on one tape interacts in a distributed nature with the other piece of the tape. Hence the difference, and hence why the new model is likely to be closer to the real charge of the tape.